we'll start off with a case study of Lorentz attractors and then also Newton's method and how they produce very different types of chaos. Uh, so if you want to go now, Julian.
Hello, can you hear me? Are you able to hear me?
Yes, everything's
Yes.
fine.
Yes.
Yeah, okay. So in 1963, Edward Lorenz developed a simplified mathematical model for atmospheric convection, and it's made up of these three nonlinear equations, where sigma represents the ratio of fluid viscosity to thermal conductivity. Rho, this symbol represents the difference in temperature between the top and bottom of a system, and beta represents the ratio of box width to box height of the system. So these three variables are differentiated with respect to time. And to demonstrate the chaotic nature of these, I've written a Python program that should be visible with graphs here. So on the right, we can see what happens with X, Y, and Z values based on these three equations being plotted over time of 50 seconds. And the values that were passed were sigma being set as 10, beta as 8 on 3, and rho as 28, which are the values that Lorenz initially used. However, in this second graph, we can see what the nature of the system looks like when we change the R value to be higher and into that of a chaotic nature. So looking at the right-hand side graph on this non-chaotic system, we can't really see much detail and point out why it's not chaotic. But if we look at the graph on the left-hand side, we can see that it's essentially just a harmonic oscillator of position to time. Whereas on this chaotic graph, we can see position and time acting completely different. So after some more in-depth testing, the minimum R value to create a chaotic system is approximately 24.75. And the Lorenz attractor in particular requires an R value of 28, which is what you're seeing in this diagram here. What I'd like to do now is ask if you have any initial values that you'd like to see so I can show the chaotic nature of the Lorenz system between a very slight change in those initial values. So either Jason, if you'd like to come up with any XYZ values, or Ajani.
Let's keep it
If
simple.
not,
1, 2, 3.
1, 2, 3. Okay. So if we start with the values of 1, 2, and 3, we'll get this system here. And if I run it again with the values of just down here, 1.00003, 2.0021, and 2.9997 or something like that, that's very close. We can see by looking at the graphs on the left-hand side that they're very different. So by zooming in here, where the blue is the X position, orange is the Y, and green is the Z, we can zoom into a similar area about 30 to 40 seconds in and notice how they're completely different, essentially, from just a slight change in initial values. this is what was called a turbulent state of the system because of the application of this Lorentz system to atmospheric convection, where this is essentially showing the reason why we can't predict the weather. These functions are used to show increased winds, cloud development, and thunderstorm development, where it's important to know that the X, Y, and Z values are not actually meant to be positions. They're just graphed for visualization. The X value is supposed to be proportional to the rate of convection, Y to horizontal temperature variation, and Z to vertical temperature variation. And these equations also arise in other models for lasers, motors, and circuits, but that's not something that I've looked into. So I hope that this has shown the chaotic nature of the Lorentz systems, even if it's only by a visual analysis of two graphs. And I think I'll pass it on to Ajani.
Hang on, let me just screen share. Okay, so for my part, what I decided to do to prove it's chaotic is, hang on, I'll stop the visualization quickly. Is I graphed out, first of all, I picked a random function. For instance, I've just picked a function with root, whoops, I think I've written this wrong way around. No, I haven't. With roots -3, +2 and 0. Just that as an example function, because the topic is about Newton's method as opposed to what functions it's applied on. So I just picked any random function. And then the way this visualization works is for every pixel along the horizontal line, it will run a certain number of iterations of Newton's method and then color that pixel based on which root it got closest to. So for instance, on 0 iterations, it's just which root is closest to any given pixel. And if you run 1 iteration, I've lost where I was. If you draw 1 iteration for every pixel, you start to get these interesting sections within sections. Like for instance, Y is what's clearly starting closest to purple is clearly tending towards green. You can start to see that appearing here after 1 iteration because of the overshoot that can occur within Newton's method. And as you continue down further and further iterations, you start to get this more and more detailed pattern due to overshoots and cyclic behavior within Newton's methods, which is quite interesting given that Newton's method is supposed to create a very predictable and standard result, and that it does find roots, however, is not very predictable as to which root it will find. So to try and make it a little bit more clear as to what's happening here, I then also created another visualization where instead of just doing the horizontal plane, I used the vertical plane for complex numbers as starting points to then as starting points for a non-complex function. Hang on. So for every pixel in this image here, it starts off with that as the initial XY position and then runs 0 or 1. It starts off with 0 iterations of Newton's method, and as time progresses, as you can see down on this bottom line, it does more and more iterations of Newton's method, showing this more and more complicated shape. And you can start to see, which you couldn't really see in the one-dimensional version, that there's this fractal behavior starting to be created. And I wasn't able to prove it within this assignment because it goes way out of scope. Like I don't have enough pages to talk about it or time. As you continue to graph the Newton's applications to an infinite number of applications, it actually ends up developing a fractal. And because of this fractal that's produced by mapping the starting positions to which root it will eventually tend towards. It means that for any given point, it is unpredictable to determine which route that point will tend towards. If you get what I mean, yeah. Yeah. Sorry.
Okay, so that's it.
I've got a conclusion. So, as
Okay,
chaos
to be brief
theory.
though, because you've had 10.
Oh, yeah, okay. So,
Please.
as chaos theory is a complicated topic, we decided to use visual analysis to show the chaotic nature of systems. And what we've showed is that the chaotic factor is not something restricted to the behavior of dynamical systems. Rather, it's something that can be observed once a chaotic state is reached within a system in general. Thank you.
All right, well done, guys. All right, well done, guys. That's very interesting. I'm actually very impressed. I can't express how impressed I am at the moment because I've got a million things still going on. I'm actually watching the other class as well while we go. So I actually feel as though I'm going to call you two back for the future if you're interested. We'll see how we go with that idea, but it's it's very good. I like the Newton's inference that you've done. I've done a bit of work on that myself, so I'm very pleased that you've done that. All right, so